Okay, today we're going to talk about something extremely important called the derivative. Most of Calculus 1 is spent talking about derivatives, so this is really important, okay? The question we're going to ask is, what is the instantaneous rate of change of a function? Look at the picture that's there. Ignore the red line for a few minutes. We'll get to that in a little bit. I want you to just look at the blue curve. Do you see that? It almost looks straight, but it's not. It's got a slight curve to it. That's a parabola, which you should know about from college algebra or pre-calculus. The equation of that parabola is f of x equals negative 16x squared plus 150. Now, it's zoomed really far in. That's why it doesn't look very curved, okay? That picture is zoomed really closely so that we can see this point right here. The point 2, 86. Where am I getting the 86 from? Let's see if you remember that. The x value is 2, so I plug that into the function, and I get f of 2, which comes out to be 86. Okay? What I'm going to do is I'm actually going to write there f of 2. Okay? Alright, so now, here's the question that we want to answer. What is the instantaneous sorry, that's misspelled. Rate of change of the function well, that moved over on its own. At x equals 2. Okay, that's the question that we are going to be asking. At that one point right there, how fast is the function changing? Okay, so that's called the instantaneous rate of change. Alright, so now, how do you answer a question like that? Well, first of all, we need to talk about what does instantaneous rate of change mean. That's an abstract concept. So let's make it a little bit more concrete. Let's say something geometric that you can actually picture in your mind. When we say instantaneous rate of change at x equals 2, what we're asking there is, what is the slope of the graph at the point 2, f of 2? Okay, so I'm just going to reword the question this way. What is the slope of the graph? Darn it. At the point two, f of 2. Okay, now there's two concerns that come up. One concern is the word slope is usually used in relation to what kind of shape? Well, when we say slope, we're always talking about lines, aren't we? Is that blue curve a line? No, I mentioned earlier it's a parabola. And by the way, here's the equation. So you see that's quadratic, so you know it's a parabola, right? So it seems strange to use the word slope for something that's not a straight line. That's one concern. Let's write that down. Okay. So two concerns. Number one. When we mention slope, we are always, well, let's use the word usually. We are usually speaking of a line. So what does the slope of a curve mean? So that's one concern, and we'll deal with that. And number two, there's another concern. When you are calculating the slope of a line, how many points do you need? You need 2 points to find the slope, right? So how are we going to find the slope at just the point 2 f of 2? Okay, so to calculate slope of a line, we need 2 points. How can we calculate slope with only 1 point? Okay, so I'm going to address those two concerns. So, concern number one. What do I mean by the slope of the parabola at the point 2 f of 2? Okay, so here's what I mean, and this is where the red line in the picture now becomes important. Okay, so it's true that slope refers to a line. I have a blue parabola that's curved. So what do I mean by the slope of the parabola at the point 2 f of 2? What I mean is this. I imagine balancing a line right at that point, balancing it on the parabola, so that at that one exact point, the red line is parallel to the blue parabola at that one exact point. Okay, that's what I mean by the word balancing. Okay, so imagine taking a ruler that's red, and you're placing the ruler on the blue parabola right at the point 2 f of 2, and the ruler balances itself on the parabola so that it's parallel to the parabola right at that one point. Okay, then when I say the slope of the parabola at that point, what I mean is the slope of the line that's balancing on the parabola. Okay, and that line is called a tangent line because it's touching the parabola in one point only. It's called a tangent line. And the slope of the tangent line, we call that the slope of the parabola at that point. Okay? So that's my answer for concern number 1. I'm going to write this down for you. Okay? So when we say the slope of a curve at a point, what we mean is the slope of the tangent line balancing on the curve at that point. Okay, so that takes care of concern number 1. So I'm going to go ahead and cross that concern out because we've dealt with that. So it's no longer a concern. Okay, but that does take us in a way out of the frying pan and into the fire, because now we have a serious problem with concern number 2. Okay, so when I say slope of the parabola, I really mean the slope of that red line. Well, definitely in order to find that slope, I need 2 points. That's how many points it takes to calculate the slope of a line. So how am I going to find the slope of that line if I only know 1 point? Okay, here's how we're going to deal with that. Let's look at a new picture. Okay, here's the same graph, just zoomed out a lot further. Okay, you can tell when you zoom out, you can see the blue parabola. You can tell a lot easier that it's a parabola now, can't you? Because when we zoom out, you can see the curvature a lot more. And here's the point that we were talking about right there, 2f of 2. Okay, so here's what I do. I move over a little bit. We're going to call that distance h. Okay, because I move over horizontally, so we use h for horizontal. Okay, so if I was at 2 and then I move over a distance of h, where am I going to be now? I'm going to be at 2 plus h. So this point right here, let's highlight these. So that, just a second here. Okay, so this point is the point 2f of 2. Then I move over a distance of h and I get this point, which is 2 plus h, comma, f of 2 plus h. Okay? Now that red line is not exactly the same red line from the previous picture, because that red line is not balancing on the blue parabola. Let's zoom in on it so you can see. Okay, there we go. If you take this area right here, okay, and you zoom in on it, it looks like that. Okay, so you see that that red line is not the tangent line that I was talking about in the picture above. The tangent line in the picture above was balancing on the parabola and only touch the parabola at one point. Okay, this line here is touching the parabola at 2 points. And if you zoom in on it, we see them here. Okay, so this is the point up here, 2 f of 2. And then if I move over a distance of h, then I have the point here, 2 plus h, f of 2 plus h. And I get a line that touches the parabola in 2 points. It's not exactly parallel to the parabola at this point. Okay, but that's okay. Let's just leave it like that for now. The point is that I can calculate the slope of that line, can't I? Because there's 2 points. So we can find the slope. Okay, let's write this down. I'll write this in red because I want you to understand that this is the slope of the red line. So I'm going to write it in red. Okay, the slope equals rise over run, right? So that's one y value minus the other y value divided by one x value minus the other x value. It doesn't matter which order I write the subtraction as long as I do it the same on the top as the bottom. So I'm going to write it like this. This y value, f of 2 plus h, minus the other y value, f of 2, divided by the x value, 2 plus h, minus the other x value, 2. Can I simplify that at all? Well, sure. In the denominator, the 2's cancel, right? So that slope is f of 2 plus h minus f of 2 divided by what? H. That's the slope of that red line. Okay? I would like the slope of this red line. I'm just reminding you here. I would like the slope of this red line that is tangent to the parabola at my point. Okay, so I haven't quite found that, have I? Because that red line is not the same slope as the red line that crosses the parabola at 2 points. But here's what we do, and this is the genius part right here. What we do is we shrink the size of h. And let's just imagine what will happen. If I shrink the size of h, then that means, let's label these as point number 1 and point number 2. If I shrink the size of h, then point number 2 will slide over closer to point number 1. And when it gets to be like, let's say here, then that line will be more like this. And when the point moves over here, as I shrink h smaller, then the line will be more like this. And eventually, what we do is we shrink h all of the way until it disappears. Okay? And let's write it like this here. Let's shrink this down a little here. If we shrink h down to 0, we end up with our original picture. Okay, so what would the slope of that tangent line be? That slope equals, so I'm going to write, oh, I covered up my H a little bit. Let me move this out of the way. There we go, that's better. So the slope of that tangent line is this, where H is shrunken down to 0. In other words, it's the limit as H goes to 0. So the slope of that tangent line is the limit of f of 2 plus h minus f of 2 over h as h goes to 0. And there you go. That is called the slope of the blue parabola at the point where x equals 2. Okay? And that is measuring the instantaneous rate of change of the function when x equals 2. Okay? Very important. Let's summarize that in one sentence. The instantaneous rate of change of f of x at x equals, let's just say at x equals c, because it doesn't have to be at 2. You can do it at any other location. The instantaneous rate of change of f of x at x equals c is the limit of f of c plus h minus f of c over h as h goes to 0. Okay? And it is called the derivative of f at c. Let's say at x equals c. Okay, this is a formula. Very important. Let's write that in red here. And there's a symbol for it. I'm going to show you several symbols, but here's the most common one. So we write f with a sort of apostrophe here. You say f prime. That apostrophe is called a prime. Okay, f prime of c equals the limit of f of c plus h minus f of c over h as h approaches 0. Very, very, very important. This is what we're going to spend most of the rest of the semester talking about, is derivatives. Okay? So now that we got that figured out, let's go back and answer the original question at the top of the page, okay? Let's go back here. Oh, by the way, we dealt with concern number 2, so it's no longer a concern. I showed you how to do that. Okay, so Let's erase this stuff and let's answer the original question here. So you can see how the mechanics work out of the calculations. Okay. So the question was, what's the instantaneous rate of change of the function at x equals 2? Which can be reworded, what is the slope of the graph at the point 2 f of 2? Okay, and here's how you do the problem. We write f prime of 2 equals the limit as h approaches 0 of f of 2 plus h minus f of 2 over h. All right, so let's do that limit. F of 2 plus h is what? It's negative 16 times 2 plus h squared plus 150. Okay, and then we subtract f of 2. Actually, I don't really need those parentheses. I'm going to erase them. So we subtract f of 2, which is 86. Where am I getting the 86 from? I'm just plugging 2 into the function, and you end up with 86. Okay, divided by h. All right, let's simplify that. So that's the limit as h approaches 0 of, okay, we have negative 16 times 4 plus 4h plus h squared. And then there's plus 150 and then minus 86. That comes out to be 64. 150 minus 86 is 64, okay, over h. This is all just algebra. You should be able to follow all of that. Okay, let's simplify it some more. Limit as h goes to 0. Okay, I'm going to distribute that negative 16, and we're going to end up with negative 64 minus 64h plus h squared plus 64 over h. Okay, this is really nice. Look, the 64s cancel out. And that ends up being super important because since the 64s cancel out, what we're left with on the top, sorry, that moves over on its own. On the top, then we just have negative 64h plus h squared over h, because the 64 is canceled. Now, that's super important because now you notice that on the top, every term has an h, right? So that means I can factor h out on the top. And let's write the top like this. Negative 64 plus h quantity times h. And that ends up being so important because those two h's will now cancel, which is great because I want to let h go to 0, and that was going to be a problem with h in the denominator. And now that problem has gone away. Okay, so now it'll be really easy to finish the problem. We have the limit as h goes to 0 of negative 64 plus h. All right, let h go to 0, and what do you end up with? You end up with negative 64, and there's our answer. So the slope of the parabola right there is negative 64. Okay? Which means that the function is decreasing at a rate of 64 vertical units for every horizontal unit. I said 64 there. I didn't say negative 64 because I used the word decreasing. The word decreasing is your negative sign. Okay? So that's how that works. And that's called the derivative of f at 2. Okay? Super important. This is maybe the most important concept from the whole semester if you judge by the amount of time we're going to spend on things. Derivatives is the largest chunk of the semester. Okay? Now, let me show you this here. What if I said to you, I want you to do the same thing now over here at 1.5, and then I want you to do it again over here at 2.5. Okay. Then you would say to yourself, okay, well, now that I understand how to do it, I guess I can do it 2 more times. And you would just change the number 2 to 1.5, do the problem again, and then change that number 2 to a 2.5 and do the problem again. Okay. Or if you're really smart about it, you can do the limit just one time without any number plugged in. Just leave the variable x there and do the limit, which is called the derivative in this case, one time. And then you can plug in all the different numbers you want to into the derivative. Okay? So this is called the what's on the screen right now is called the derivative of f at 2. Okay? You could do that at as many different points that you want. There's also what's called the derivative function. And let me show you that, okay? Let's get this stuff here. We don't need that anymore. If you want to do the derivative at many different places, then it makes sense to do the derivative without plugging in the number 2, but leaving the variable x there. Okay? So the derivative function okay. This is a function that tells us the instantaneous rate of change of f with respect to x. Okay? And it's just the same thing I showed you up above, the derivative. The only difference is Instead of using a specific number like 2 and writing f of 2 plus h minus f of 2, I'm instead just going to write f of x plus h minus f of x, okay, over h, and I'm going to call that f prime of x. Okay, so let's do that for the example up above. Remember, in that case, f of x was negative 16x squared plus 150. So let's find what's called the derivative of that. This is going to be very, very similar. Excuse me, very similar to above, okay? I'm going to write f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x over h. Okay, let's work that out. So that's the limit of negative 16 x plus h squared plus 150 minus negative 16x squared plus 150 over h. Now just a bunch of algebra. So that's negative 16 times x, is it? Yep, that's right. X squared plus 2xh plus h squared plus 150 plus 16x squared minus 150 over h. And then distribute that negative 16 in the front. So we'll get negative 16x squared minus 32xh minus 16h squared plus 150 plus 16x squared minus 150 over h. Let's see what we can get rid of. The 16x squareds disappear and the 150s disappear, which leaves us with very little on top. And the important thing to notice here is that everything on top has an h in it. So I can factor h out on the top. And I can write negative 32x minus 16h times h. And the reason why that's so important is because now that h that I factored out will cancel out with the h on the bottom. We're almost done. So we finally simplified down to this. Okay. Now you do the calculus. Now that the algebra is done, you do the calculus, which is what? Let h go to 0, and what do you end up with? Our answer is negative 32x. Okay, so I'm going to write that over here. f of x was negative 16x squared plus 150, and we calculated the derivative of f, and we write f prime of x equals negative 32x. So now if you wanted to find the instantaneous rate of change at 2, like we did earlier, we were asked that question. Okay, and now it's really easy. I can just say f prime of 2 equals negative 64, which we already knew because we did that problem before. But here's the beauty of it. If somebody now asked you for the derivative at 1.5, you don't have to redo all of the work. All you have to do is plug 1.5 into the derivative function. And what would you end up with? You would end up with negative 48. And so if somebody asked you for the derivative at 2.5, you just plug in 2.5 into the derivative function, and you would end up with negative 80. See, I could do this all day long. So if you look back at our original picture, let's zoom in on this. Okay, at this point right here, the function is decreasing at a rate of 64 vertical units for each horizontal unit. It doesn't look that steep, does it? But it is. 64 is how fast that's going down. Okay, the derivative is negative 64. Here, we found that the derivative is negative 48, so that means that the function is decreasing at a rate of 48 vertical units for every horizontal unit. So no matter how far you move horizontally, you go down 48 times as much. It doesn't look like it again because the scaling of the axes, just look at this. From there to there is only a distance of 1/2, but from here to here is a distance of 50. They've used a different scale on the y-axis than the x-axis. That's why it doesn't look as steep as it really is. Okay. Over here, we got a derivative of negative 80, which means that the function is decreasing at a rate of 80 vertical units for every horizontal unit. Okay. So here it's decreasing at a rate of 48, the derivative is negative 48. Here the derivative is negative 64, so it's decreasing at a rate of 64. And here the derivative is negative 80, so it's decreasing at a rate of 80. You see the function's getting steeper and steeper the further to the right you go. Okay, so that's derivative, very important. Now we're going to spend an awful lot of time on this because there's a lot more to say about it. Okay, but at least now you know the basic of what derivative means and how to calculate it. And if you're ever asked, what is the definition of f prime of x? This is the answer right here. That's the definition of the derivative of f. Okay? I'm going to say that again. That is the definition of the derivative of f. This other one that I wrote in that red box, that's the definition of the derivative of f at x equals c. Okay, very, very important. Oh, and before I close off, I want to show you, this is important too. There's more symbols than just the prime. There's other symbols that you can use too. Okay, this is on page, I have to find it real quick here. If you were to go in the book to page 84, you will find several different symbols for derivative. Okay? So these all mean the same thing. So the one that I used was f prime of x. Okay? You might sometimes see this instead. You might sometimes see y prime. Well, that makes sense, doesn't it? Because f of x and y are the same thing. So f prime of x should be the same thing as y prime. Okay? So that's pretty straightforward. But there are other symbols that you'll see sometimes too. Like this one, which I'm not going to explain right now, but I'm just write it down for you because you'll see it sometimes. dy over dx. I will explain to you who came up with that symbol and what was their reasoning later. Okay? And another symbol would be, since y is the same thing as f of x, you can also see this df over dx. Or like this, d over dx with an f next to it in parentheses, or a y next to it in parentheses. These all just mean the derivative of f. All of them mean the limit as h approaches 0 of f of x plus h minus f of x over h. They all mean that. Okay? That was a longer video, but we're done for today.